it was interesting because I didn't, many of you decided that you were going to take this subtraction problem inside the parentheses and actually change both of those expressions, those terms that have a fraction in it, rational expression, and change it to 12s, which I hadn't really seen much of that before. So it was interesting that a lot of you did that. There's absolutely nothing wrong with doing it that way. Nothing. However, there may be, if it works for you, a simpler way to do that, because what most of you did is you converted both of these denominators to 12, and you multiplied the top and bottom of this first fraction by 3 in order to make it 12 on the bottom, and to keep it an equivalent fraction, multiplied x plus 2 by 3. And then similarly here, you multiplied the numerator and denominator by 4. So you ended up with 12 as the denominator, did your work by simplifying the two numerators, and then canceled the 12 out at the end to get the opposite of x plus 10, or negative 1x plus 10. Another approach to that is to simply use your distributive property and to say 12 times this and 12 times that. So another approach would be to just say 12 times exactly what you have there, x plus 2, and now the whole thing is divided by 4. And then to keep your subtraction sign, and then 12 times the fraction that's there, x take away 1, the whole thing divided by 3. So now you can, because you have in each of these terms here, you have a denominator that will divide into the numerator evenly. That means they each have a common factor of 1. So now you could reduce instead of at the end. And for some people, this is a little easier in terms of the number of steps that they have to do. So there's your 3 that many of you ended up doing at this step when you multiplied top and bottom by 3. So you're just kind of doing it at a little different stage of the problem. And here you have your 4 that you ended up when you multiplied the top and bottom of this by 4. But what's nice now is your fractions have disappeared. You have 1 on the bottom. So this is really what you end up with, 3 times x plus 2, take away 4 times x minus 1. Okay? And then the only problem that arises from at this point is distributing that negative through. So here you have negative 4x plus 4. That tends to be the only other mistake that students make at this point, and that's negative 1x plus 10. Any questions on that one? Okay. This next one, again, it's the same reason for doing this problem. Number one is to check your order of operations and also to make sure you're distributing that negative sign. That's the purpose of my putting this problem here. Again, it's the kind of thing you would have done in previous math classes. But again, if we think about the idea of terms, we really don't need to even know the order of operations, because as you can see here, once I separate my terms, which is the pieces of an adding and subtracting problem, the expression on the left side is just one term. And in order to simplify that, I have to multiply and use my distributive property. So that's 3x plus 6. Nothing's going on with this one. It's just basically plain old 10. So you leave that as it is. And now you have to use your distributive property here. So you have two choices. You could either distribute the 5 as it is and then subtract both of them, or the reason why you can call that a negative 5 is because subtracting 5 is the same as adding negative 5. So that's why it's legitimate to call that negative 5. So now you have a plus, you have an addition, and now you multiply both of these by negative 5, and you get negative 5x plus 20. So again, that might be the one area, if you had any problem, that's one of the places it can arise. So check your work and make some notes if that's where it happened. So the left side can't be simplified anymore. The right side, you have two like terms, you get a 30 there. And now I'm just going to simplify this notation and call it minus 5x. So I'm going to bring my 5x to the left side by adding the opposite of negative 5x, and I get 8x. I'm going to subtract 6 from both sides, I get 8x equals 24. I divide both sides by 8. X equals 3. And this is usually how you're used to writing it. You're used to writing, again, notice you start with an equation. At every single step, you're writing what we call an equivalent equation until you get to your very last equation, which is the simplest that you could write. So every equation is solved by writing a series of equivalent equations. And I'm only emphasizing this now because when you get to quadratics, you tend to leave off your x until the very end. So every time you're solving an equation, when you look on your paper, at every step, you should see that equal sign with an expression on both sides until you get down to the simplest equation that you can possibly arrive at. Now, this is new notation for a lot of you, the solution set is, and that's because we're just used to writing a final equation for our solution. But every equation will either have, you could have an equation with no solutions, not zero, but no solutions, 1 solution, 2 solutions, 3, depending on the degree of the equation, the highest exponent. And also, an inequality has an infinite solution set. So every answer that you get, every solution is part of a set. That's called the solution set. So for my math lab, and when you check any equation in the back of the book, this will be the notation that you see. We know that those curly braces represent sets, and that 3 in there says, I am the one number in the whole world that makes the left side equal the right side. And most of you found that. I think you got 15 equals 15 here, right, when you checked it? Okay. All right. And I went around the room and looked at how most of you solved this equation. This equation, the name for this equation, so that you know what we're talking about, and this is part of your title for today's class, is called a rational equation, because it's a fractional equation. And right now we're a little lucky because the denominators are all constant numbers. So we can look at those numbers, and in our head we usually find a multiple. If I were, let me just cover up the whole left-hand side of this equation, including the equal sign. If I cover that up, I think there's a way to do it here. Let's see if I can find it without taking too long. And I think if I click on that, I can fill it. Where's the filler? I don't know if that will fill it. Yeah. Okay. So let's suppose I just kind of move this so we can't see that. If I gave you this right-hand side of the problem, that's no longer an equation. And the only way you could combine those two fractions is to make common denominators. In this case, it would be a 6. So you wouldn't have to change this one at all, and you would multiply top and bottom of this by 2, okay, 2 over 2. The fact that this is an equation, you're going to have available a very powerful tool that you don't have when you're just adding and subtracting. You have two sides now, and you have the right with an equation to add the same quantity to both sides, subtract the same quantity, multiply by any non-zero quantity, and divide by any non-zero quantity. So when you look at those three numbers and you think of a multiple of 4 and a multiple of 6 and a multiple of 3, there's an infinite number of multiples. We try to find the smallest to make our multiplication as easy as possible. When it's numbers, it doesn't really matter whether you call that 12 or 24 or 36. But when your bottoms are all algebraic things like x minus 2 and x plus 3, if you don't find the smallest multiple, then it gets to be this like horrendous multiplication problem. We want to avoid that. So we try when we're working with numbers to look for the smallest so you understand the idea when we come to the algebra. All right, most of you, this is what I saw. I saw stuff like this on your paper. Nothing wrong with that. But often when this becomes an algebraic situation, you could stop right here and do something, and this is where students kind of get stuck. Do you see that the only way this left side is going to equal this right side is for you to find the value of x that makes the two numerators equal? Do you understand that? Do you see that the denominators are already equal? 12 equals 12, right? There's nothing to solve there. You don't need it. You don't even need it. Because all you have to do is make the numerator on the left-hand side equal the numerator on the right-hand side. So now it just becomes a nice baby linear equation that you knew how to solve before you came into this class. 7x equals 7, x equals 1. All right. So what I'm hoping to do today is to break you of the habit of having to convert everything to common denominators when you have an equation. Because there's an easier way to do it, or maybe not easier, but at least something that involves a few less steps and might be easier to see. So I started with the teaching demo. Notice I started with the exact same problem we just have. And if you agree with this statement that it's easier to solve linear equations without fractions, and is there a way to solve linear equations that contain fractions without having to deal with them? The answer to both of these questions is yes. When you see something like this, you would be much happier if you never saw the denominators at all. So rather than reverting back to techniques that I'm glad to see are well ingrained with adding and subtracting fractions that you need to make them look like, but notice what I'm saying with adding and subtracting fractions. We're not adding and subtracting fractions here, we're solving an equation. And because we're solving an equation, we have a very powerful tool, and that is I can multiply both sides of this equation by any number in the universe except for 0. Now I'm going to try to pick a number that's helpful to me. I'm not going to pick negative 362. That's not going to be very helpful to me. All right? Although it might be, it probably 362 negative, is that divisible by 12? No, good. So that wouldn't have been helpful. So the first thing I want you to recognize and try to bring to your mind is the fact that this is an equation. It's not an adding and subtracting problem with fractions. Once you have an equation, you can multiply both sides of the equation by any non-zero quantity. In this case, I'm just showing you the process in case you've never gone through it. I really, in our mind, what we do when we come up with 12 is that we're prime factoring each of those numbers. 2 times 2, and 6 is going to borrow one of those 2 and become 3 times 2. And then 3 is right there, it's already included. So when you just multiply right through those circles, 3 times 2 times 2, that's your common multiple. So 12, we know it just by being familiar with multiplication tables. But what we do is we take each prime factor that we see, which in this case is only a 3 and a 2. 6 doesn't work because the number 4 has 2 of those factors, so it's 3 times 4. So what you do is you take your original problem, x plus 1 over 4, and anytime I see a numerator that has more than one term, and if you've been in this class, if this is your 4th class by now, you know what I mean by terms. It's the pieces of an adding and subtracting problem. So this numerator has 2 terms, I put it in parentheses. My next numerator, the first term on my right side, only has 1 term in the top, but again, my second fraction has 2, so I put it in parentheses. So that's kind of like something that I do without even writing down, so I'm just going to put it there as step 1.5, okay? Or maybe step 1/2, since this is our first step. So I'm going to take each one of those pieces of the equation and I'm going to multiply it by 12, which means I just have to put it up in the numerator. I don't even have to put 12 over 1. Okay. Now, why do I do this? I do this because right now I can get rid of those fractions. I can get rid of those denominators right now. 4 goes into 4 once, 4 goes into 12 3 times. 6 goes into 6 once, 6 goes into 12 2 times. 3 goes into 3 once, 3 goes into 12 4 times. So right now, this becomes 3 times x plus 1 equals 2 times 1, which is 2, plus 4 times 2 minus x. So that's the answer to the y right there. I now create a linear equation just like I like them, with all ones in the denominator, so I don't even have to put it in. It looks like I don't have denominators. I really do. It's 1. But this is how we like to see linear equations, because we've spent plenty of time in our lives solving these. So now that you've created an equation that's equivalent, this equation is exactly the same as that one and is exactly the same as that one. You've created another equivalent equation. Now you can go to town and do what you normally do. Use your distributive property. Okay, and let's do this. We get 3x plus 3. I'm actually doing all these steps here all at once, okay? I'm already past this step right here. So I'm down to here. 3 times x plus 1 equals 2 plus 4 times 2 minus x. That's 3x plus 3 equals 2 plus 8 minus 4x. So I kind of talked through all those other steps there. Now we're going to combine like terms. There aren't any on the left-hand side. And on the right side, we have 10 minus 4x. Okay, we add 4x to both sides. We get 7x. We subtract 3. We get 7, and x equals 1. And there's our solution set. Okay. So it says you can check your solution. You go back and you can throw it in. I would suggest you get used to doing that, because any help with fractions, so this is 2/4 on the left side. So you put it 1 in and you get 2/4 on the left side, and on the right side you get 6 plus, what is it, 1/3? 1/3. And this will just help you a little bit. So 2/4 is the same as 1/2. 1/3 is the same as 2/6. Is 1/2 the same as 3/6? Yep. And a nice way to check that, because this is something we're really weak in our culture, is that this is called a proportion. Any equation that has one fraction on one side and just one fraction on the other, whenever they're equal, this property is always true, that 1 times 6 will equal 2 times 3, and that's how you could always check a proportion. All right. Solve graphically. What the heck do I mean by that? Solve this graphically. Wow, how would I do that? Well, we talked the other day about graphing calculators and finding solutions. So let me just show you how you could do this graphically. What you would do is you would take, just in case you have a graphing calculator and you want to check your work another way, you would take the left-hand side of this equation, this side, and call that y1 equals. So you say y1 equals, and this is where your parentheses come in, x. So you can always think, if I had to put this in a calculator, would I need parentheses? And if the answer is yes, it's probably a good idea to use it. X plus 1 divided by 4. So that's my one equation. Here's one equation. I can graph that, and I will get what kind of picture for that, this type of equation right here, x plus 1 over 4. Kind of equation. Linear, right, because x, the highest power on x is 1, right? And then you take this thing, and you make that y2. You can write it just like it says. So go down here and you say, okay, I've got 1 divided by 6, and I'm going to add to that quantity 2 minus x. I think I want to put 2 sets of parentheses here just in case. Never hurts to have too many parentheses, as long as you keep track of them. Divided by 3, and my parentheses, that's my second equation. So when you solve this equation for x, you're saying, when does this equal that? When does this straight line intersect that straight line? So if you were to graph this, there's the first line, and there's the second line. And that intersection point right there, let me get a little picture of this. And of course, I'm going to lose my calculator again. Anybody got any tricks for me here? come on. Yeah. All right, so if I take a picture of that, right, where that intersects should be what number? What should be the number where those two lines intersect? What value of x? 1, right? So let's take a look at this for a second. I'll get you in a second. I just want to cut this and put it back on the page we're on. All right. Paste. So that would be the picture. And, you know, how would you get the number 1 if you didn't know the answer? What could you do on your calculator to get the number 1? Well, you could look at your table. If you know, jeez. Yeah, okay. You could look at your table. Well, that's one idea. Let's take a look at our table. All right, when x is 0, that's the left-hand side of our equation, and that's the right-hand side. Nope. So if your answer happens to be an integer, and your window is set to change every 1, you're going to be in luck. If it's a funky answer like 0.333, you're not going to be in luck. So right here, your table tells you that when x is 1, the left-hand side is 0.5 and the right-hand side is 0.5. So you know that's your answer. The intersection point, the value of this intersection point right here, the coordinates would be x is 1 and both y's would be a half. Now, how else could you do it? The other way you could do it is to use a command. See this little yellow thing here? It says calc, C-A-L-C. If you go to your calc button, you can say, where do these two lines intersect? We did this on Monday. And this is the nice part. You don't even have to guess. Once you get to here, you can say, enter, enter, enter. And voila, there's your answer. X equals 1. Did you have a question, Jude? Okay. All right, so you have both a graphical way and you have an algebraic way now to solve these types of equations. Again, your tendency will be to change everything to 12s, change the numerators, and go from there. But what happens is a lot of students, when they get their 2 equivalent fractions, they don't know where to go. So I want to show you another approach in case you ever get there. Remember we had this, and we had the 12 here, and we had the 12 here? Remember we had that, and I just took away the 12s? What kind of equation is this? What name do we give to this equation? It's linear, yes. And I just gave it a new name, or what I told you we were all weak at a minute ago. It's rational proportion. It's a proportion, just like 1/2 equals 3/6. You have 3x plus 3 over 12 equals 10 minus 4x over 12. This is a proportion, folks. So the same properties apply. You multiply 3x times 12, 3x plus 3 times 12, and you set that equal to 12 times 10 minus 4x. And then you solve it, you'll get the same answer. Not necessary, but I just want you to see that it works that way as well. All right, let's go on to the algebra type ones. Okay. So we've just solved equations with constants in the denominator, but now we got to think about what happens when we have denominators that look like this. Denominators that have algebraic expressions and that have variables as part of it, not just constants. Okay. So the procedure for solving these equations is similar to the linear equation we just solved. To solve these equations, we are going to multiply both sides. But I prefer not to call it a lowest common denominator anymore, because what does that set you up for? It means you're going to change everything to common denominators. Remember, the number you create as your common denominator, your lowest common denominator, is the lowest common multiple. So I'm going to be, when we're dealing with equations, I'm going to be talking about the lowest common multiple. There's one important difference between solving equations like this and the one we just did. We have to, at the very first step, say, what value of x would make that denominator 0? That can't be part of your solution set because it's not part of what you learned in your class activities called the domain. Okay, so when we look at this equation right here, there's only one number that's going to, two numbers actually, that's going to make x, the denominator, equal 0. And why did I say 2? Because I take my first, so you take each denominator. To find those excluded values, you take each denominator and you set it equal to 0. So I take my first denominator, and this is what you do, duh, right? Duh. It's not, I know what x can't be here. X can't be 0, because when x is 0, that's 0. So x cannot be 0. And then you say, well, isn't it just 0 for the next one? Because 0 squared minus 0 is 0. Yep, 0 won't work there either. As long as it doesn't work in one of them, it doesn't matter. Then, however, in order to see all the possibilities, because remember I told you when you have that little 2 up there, you could have 2 possible answers. So in order to see both of them, you take each denominator and set it equal to 0, but you also should factor each denominator. Well, we didn't have to factor the first denominator because x is prime. But the second denominator we can rewrite like this, x times x minus 1. So if I factor that, that's what it looks like. So when I take the second denominator, here's my first denominator. My second denominator is x times x minus 1. I set that equal to 0. My first factor that could make this 0 is x equals 0. Well, I've already got that up there. My next factor is x minus 1 equals 0. And when I solve that for x, what do I get for x? X equals what? 1. I add 1 to both sides, right? So the two excluded values here are 0 and 1. So if you do all this work and you end up with a solution that is 0 or 1, you say this equation has no solutions in the world. Because right at the first step, you know that 0 and 1. If you went back to check your answer, you'd get a denominator of 0, which doesn't represent any number at all. So let's do a little review. If I asked you how I would represent the domain here for this equation, you could use set builder notation and say it's the set of every single real number in the world called x, such that x cannot equal 0, x cannot equal 1. That's how you could write the domain with set builder notation. If you were using interval notation, you'd go from negative infinity to 0 with a parenthesis, because we can't include 0. So all the numbers to the left of 0 work, as well as the numbers from 0 to 1, as well as the numbers from 1 to infinity, all with parentheses, and you'd have to put a little union sign because you're taking all those sets of numbers and putting them together. So that's how you would write the domain with interval notation. And this is the type of notation you have to use on MyMathLab, is interval notation. All right, so let's do this problem. All right, so I did something visually. I don't know if you noticed. Did you notice how I used 2 different colors when I factored the denominator? Did you notice it, or it didn't really strike you at all? Some of you, yeah? Yeah. Why do you think I did that? Just because I like playing with colors? What do you think? Yeah, I like playing with colors. I do. I really do. In fact, I should probably put right now today, starting today, those little toolkits on your table, because colors are amazing in terms of helping you see things using different colors. But most of you won't want to change your habits, right? Just to make me happy. Even if I tell you it will help you, you'll just do what you always do probably. But anyway, I can only encourage you to use colors. All right. Why do you think I used colors on the second one? Why do you think I used a blue for x and a red for the factor x minus 1? Yeah, Jake? They can cancel out. What do you mean by that? I'll end up multiplying it, yes. That's true. I agree with that. And we'll end up being able to cancel it. But why do you think I wanted to distinguish those? Jameson? Yeah, this x here is the same factor as this one, right? So I've already seen it before. But what about this one? It's new. It's different. So this tells me how to make my multiple. So I want to show you something. I'm going to make x equal 4 in my mind. Not that that's the answer. And this is what it would look like. So it would be 1/4 plus 1/12. Do you see that 12 is already the multiple of 4? Can you see that 12 is the multiple of 4? It is the lowest common multiple because this denominator contains that denominator. You don't have to do any work to find the lowest common multiple. It's already right there. Here it is. So go back to numbers and you can see it a little easier. All right. So, but here's how you create a little visual for yourself to find a common multiple. You take your first denominator, in this case x, you put it in a circle. That's called a Venn diagram. To create my next denominator, once it's factored, I'm going to share that x, because it has an x in it too, but I must add my new factor. That's why I use a new color. And straight across, there's your multiple, x times x minus 1. That is your lowest common multiple, x times x minus 1. Both of these factors are prime. You can't factor x and you can't factor x minus 1. Okay, so let's go to town now. And to go to town doesn't mean that I create common denominators. I want to get rid of them. Get rid of them. So here we go. I'm going to multiply the first fraction by my LCM. I just create one big long fraction bar, and I multiply the top by it. I don't have to multiply the bottom by it because I'm now multiplying both sides. So my LCM is going to be this thing, x times x minus 1. So I multiply my 1 on the top by x times x minus 1. I wouldn't be allowed to do that if I didn't have an equation. Yeah?
Confusion slightly. So the first number is 1/x.
Okay, let me write it this way. Okay, here's my first fraction, 1/x. Here's my second fraction, 1/x times x minus 1. And my right side is equals 5. So I'm going to multiply both sides of the equation by this. Okay, so I'm going to multiply this side, everything on both sides. That's the key, everything. You can't just multiply one part of your equation. So there's my first fraction being multiplied by that. And if you want, I can put it over 1. My second fraction is going to get multiplied by exactly the same multiple. And I'll put it over 1 just so nobody's confused. And don't forget the right side. The right side needs to be multiplied by 2. All right. If you want, you can put that all over 1. It doesn't matter. Now get rid of those denominators. X goes with x. So what have you left with? 1 times x minus 1, which is just x minus 1. That's my first term now. So this 1/x has become x minus 1. And this is what Jameson referred to, or Jake, I can't remember. This whole thing cancels. Do you see? Whenever you multiply your fraction by the actual denominator that's there, they're just going to become a 1. And the only number you have on top is 1. So there you go. And what do we have on the right side? We have 5x times x minus 1. All right, so we're almost done here. We have x on the left-hand side because that goes to 0. And we have 5x squared minus 5x on the right-hand side. Do you have a question, Streeter? Right here? Yep. Yeah, that was x squared minus x. So I pulled the common factor of x out. And that's what I have left. Because if you multiply this through, you get your x squared minus x. Okay? You always factor. Yeah, but in the first situation, there was no way to factor the x. Okay? Yep, Jake? What are we in on the left side or right side? Right here? The second term? Yep. See, I have x over x. Yeah, so this becomes a big 1, and 1 times 1 is 1.
Yeah, I know, it's just kind of hard. It's just itself.
Yeah, it's just itself, right? Yeah, so most of us, we're not in the habit of putting a 1 here times, but that's really, in fact, we got a 1 here as well, and we have a 1 here as well, and we have a 1 there as well. So what you're really getting here is 1 times x minus 1 times 1, which is just x minus 1. So if you get used to putting the 1 with the times after it, then you'll see that whatever's remaining there from the beginning is what you end up with for the second term. All right, what kind of equation is this? Quadratic. So you have to get 0 on one side. And the only way you're going to solve this quadratic is through factoring or the quadratic formula. So we haven't done the quadratic formula yet, but factoring was P5 in your book. So remember, your greatest common friend, GCF, is x. You pull out your x and you have 5x minus 6. Your two solutions are x equals 0, but you know x can't be 0. From the very beginning, the first step of 5x minus 6 equals 0. So when you solve that, you get x equals 6/5. So that's your answer. So for MyMathLab, you do little curly Q's and you put 6/5 in. 6/5, so 1 1/5. I think MyMathLab wants it as an improper fraction. Which part? But from the very beginning?
No, like this factoring.
Oh, here?
Yeah.
Okay. So when I see 5x squared minus 6x, I always ask myself as my first form of factoring, is there a factor common to both? And I see an x. So when I pull an x out of this thing, and you can think of what that means by just saying if I divide that by x, this x cancels with that, and I have a 5x left. Okay, so x times 5x gives you 5x squared. And when I pull a 6x out of, when I say pull, it's dividing. When I divide 6x by x, I get a 6. So here's my multiplication problem. This is like a times b equals 0. So the only way this side can equal 0 is if a is 0, x equals 0. But at the first step, we said x couldn't be 0 because it made the denominator. Or when b is 0, which is 5x minus 6. And I just solved that by adding 6 to both sides and dividing by 5. Okay. Any other questions? If I go too fast, just stop me. I make some assumptions because it's 107, but I don't care if you need to revisit something. It's okay. But just if I don't hear from you, I'll just kind of go at my own pace, which may not work for you. So just let me know. I'm happy to answer any question. All right, so that does it. You're all set now to start your class activity and try these things on your own. I just want to mention a couple of things quickly about the project. Yeah, the project is due on Friday, and I've asked you several times to read your syllabus. Your syllabus talks to you about projects. Projects are due at the beginning of the class period. Otherwise, they'll be considered late. So if you wait to the very last minute, like being in the studio at 8:15 to print it out, and you're having problems printing it out, and you have to go running around the college, and you come in at 10 or 9, it's late. It's due at 8:40 on Friday. No projects grades are going to be dropped. So if you decide not to do one, it will be a 0. If you are ill on the day a project is due, you should email it to me. You could take a picture with your camera and email it to me, scan it and email it to me. If you have it done on time, it needs to be scanned and mailed to me by 8:40 on Friday. Unlike other Math 107 teachers, I will accept a late project. I will accept it one class period late. That would be Monday, but it will have a 20% decrease. So out of 60, I think it's 60 points, you would start with 48. Okay, so you just have to decide with time management how to do this project so that you're not waiting to the last. I've already had 3 students come to me and ask me questions since Monday, and they were like almost done with the project. So I'm again just trying to encourage you not to be late. I understand sometimes you are late with stuff. It will have a penalty. Okay? Are you clear on that?